up next is Martine and Dane. They're from Facebook, and they're the founders of Presto, and they're going to talk about Presto at Facebook.
Hi everyone, I'm Martine. Dane's over there. I'd like to thank Teradata for organizing the meetup. It's something that, if it hadn't been for them, it would have been very hard for us to organize one on this side of the US and fly over and all that. So, all right, so we're going to talk about how we're using Presto at Facebook, some of the major use cases, and we're going to cover how we start. Next slide. We're going to talk about how we some of these cases we target in the beginning, and then how we expanded Presto to support other things. And then Dane is going to finish with an overview of one of the recent use cases and some of the technology we're building underneath Presto in order to support that. When we built Presto in the first place, we were targeting ad hoc interactive queries. We had a big issue at Facebook where we had hundreds of data analysts that were doing, trying to do ad hoc analytics. Like their day job was to run ad hoc analytics against the Hadoop warehouse using Hive, and that was taking. It was very, very inefficient for them. It took them. It was one of the people at Facebook said, "Oh, it's a good day when I can run 6 Hive queries." So clearly that's not good for their productivity. It's a waste of time, waste of people time, and so on. So very quickly after we wrote the first version, we added the connector interface to Presto, and that opened up a bunch of opportunities. We implemented some integration with other systems, other internal data stores, and other technology that we built that allowed us to tackle other use cases that we couldn't do with Hadoop and Hive because of the latency and the cost of running queries against those systems. So I'm going to start with talking a bit about how we use Presto for the Hadoop warehouse. At Facebook, we have several hundred petabytes of data, and we can't fit all of that data in a single data center. So we're forced to partition that across multiple geographic regions. And that poses an interesting challenge, like how do you run queries across all of those? It's something that we don't tackle today, but we try to make it easy for our users. We deploy multiple Presto clusters. Each of the clusters is co-located with each physical Hadoop Hive cluster. And then we have a layer on top that can redirect users to the right cluster based on what catalog and schema they're trying to query. So in that diagram, you can see there's that gateway. So clients come in, they send a query to the gateway. The gateway implements the same interface. So the gateway implements the same interface, wire interface as the coordinators in the Presto in the Presto clusters. And based on it looks at the current catalog and schema and redirects the client to the right cluster. So it's a very simple redirector layer, but it helps our users run queries without having to think about where should I connect to and so on. Inside a single cluster, inside a single Hadoop cluster, we have each machine has a Presto process co-located with a Hadoop data node in some machines, and other machines run a data node together with MapReduce task tracker. We have to split them up like that because we found that if we try to mix up the Presto workers with MapReduce, they compete for resources, and MapReduce either makes experience pretty terrible for Presto users, or Presto tries to use all the CPU, and then it causes MapReduce jobs to fail. So we kind of forced to do that split. So some of the stats, these are correct as of middle of the year, so things have grown since then. We're running, we have about several thousand users, internal users. This includes people running queries directly against Presto or through interfaces like dashboards that hit Presto directly, or other tools that hit Presto to run queries and produce data and present it to users. Those users run millions of queries every month. This is across all the clusters that we run Presto on. And they scan several petabytes every day. And this has grown, I think since the middle of the year, has doubled in size. And that data is like trillions of rows. In terms of, there's millions of queries that run every month. Queries tend to take anywhere from a few seconds to tens of minutes, and in some cases, people run queries that run for hours. At any given point, we see about 10 concurrent queries, tens of concurrent queries, sorry. It goes from, it ranges between 10 and a couple hundred, depending on the cluster, depends on time of day, and some clusters support different workloads that have longer running queries with more concurrency. So as we built Presto to target the interactive ad hoc use cases, we had to build in some features that either made queries run at all. Like there were some queries that people were trying to run on Hive that just didn't run on Presto. For example, we had tables that have millions of partitions and millions of files on HDFS, and trying to enumerate them all up front and loading the metadata for those was so big that like even Hive couldn't deal with it. So we implemented Presto to support pipeline execution, pipeline enumeration of partitions and of splits, so we can start processing as soon as Presto discovers some splits from HDFS, and then it doesn't have to hold on to the metadata beyond the processing of each of the splits. People care about getting results quickly. In some cases, we can produce results as soon as the data shows up in Presto, even for long running queries. In that case, we stream the results out to the client, to the users, so they can very quickly start seeing samples of data if they need to. And then we've had to build other features like admission control. We have thousands of users using it every day. We need to make sure that no one causes a bad time for other people. Some people write scripts and send thousands of queries in one shot, so we need to make sure that they get properly prioritized and blocked at the source. They get throttled until they have a limited number of concurrent queries they can run. And then after that, there's resource management. We implemented some basic prioritization to make sure that small new queries get some resources and can go through quickly, and longer queries that kind of share the resources more evenly. And of course, like the system has to be up. So we've done a lot of work, and this is a piece of work that piece of Presto we focus on continuously. We make sure that the system is reliable. We try to make sure the system is as reliable as possible. Like tune the system, tune the GC, change the code to make sure that we don't run out of resources, causing other problems, and so on. One of the things we started doing recently is tackling batch workloads. We have an internal a team at Facebook that was running Hive pipelines, and they had a huge backlog, like 2,000 reports. They run reports every day and every week. And they had like 2,000 reports in the queue. Each report takes several hours to run. So we told them, hey, try moving over to Presto. We'll set up a cluster for you. And they did so, and in 3 weeks, we ran through the entire backlog, and now the cluster is pretty much idle most of the day. So, I mean, if you look at the numbers, we see there's an improvement of more than 6x in terms of CPU efficiency. Like we need 1/6 of the machines, and queries take a lot less time to complete. So we're starting to tackle more of those workloads, and as we do that, there are some features that we need to support that people rely on, like from Hive, like insert override. So we're trying to come up with a replacement inside Presto. More data types. We support only a few data types. They are extensible in Presto, but we don't support all the types that Hive supports. And then people at Facebook need custom. There's a bunch of custom UDFs they rely on, like for specific functions they need to perform on their services. And support for partitioning, bucketing, all those things are things that some of the pipelines depend on, and we need to, we're going to be working on that soon. My next big area is using Presto for user-facing products. So this is Presto sitting right behind a UI that's serving end users. Like think of advertisers. They want to do analysis of their advertising campaigns and so on. They want to break them down across different dimensions. They want to get a report. And so the requirements are different in terms from what people expect from the Presto over the warehouse. Query had to be very fast, and it had to be consistently fast. And the system has to be available like pretty much 24/7 and with almost no downtime. Some of the applications that use Presto in this manner need update semantics. They typically pre-aggregate some of the data, and they submit the data to Presto, and they keep overwriting the data, like we say counts for a given hour, and they keep updating until the hour rolls over, and so on. And some of those applications, because of the way they model their data, need to do queries that have 10 to 15 joins in them. So what we did for this is we took advantage of the connector interface and built a backend that uses MySQL. We sharded MySQL here. We take the data, we insert it into a bunch of MySQL instances, partition in different ways and organize in different ways. We actually support organizing the data in multiple ways for a given data set, so we can optimize for the queries that those applications submit to the system. And there's a separate process for loading data in because Presto doesn't support updates today. Eventually, this will fall into Presto itself. With this setup, we've been able to achieve like more than 4 nines of success rate for queries, and pretty much 100% system availability. There's no downtime. Like we have it's a multi-region deployment. If one region goes down, the other one takes over pretty transparently. So it's been pretty successful. Depending on the application, we run anywhere from 25 to 200 concurrent queries with spikes up to, almost 1,000 or so. And the number of queries per second varies from 1 to 20, spiking to I think it's like 200 or so, depending on, again, the application. And queries run consistently between, say, it's less than 50 milliseconds to about 4 or 5 seconds. Again, depending on the use case. And there are some installations where queries take, the median time for a query is like 60 milliseconds. And they're small data sets, but still, it's like, we're able to deliver that performance consistently. Right. We've been working on supporting other use cases, and we built new technology for that. Dane is going to talk about that now.
Shirking your duty there. All right. Okay, so this is another different installation from the warehouse installation and the installation we have running on sharded MySQL. So in this installation, we have large data sets, not large like the warehouse where they're these crazy huge installations, but much larger than we can afford to keep in our like sharded MySQL installations. So in sharded MySQL, like we're lucky if we're going to get like a 2-to-1 compression ratio. In these systems, we need to have data that's dramatically bigger that we can store in our installation. So we're using a custom columnar store in this case, and we see, of course, clearly much better compression ratios, 10 to 40x or something like that. Very standard for a columnar store. We need our queries to be in the seconds to minutes range, so a little bit lower latency than the sharded MySQL, but higher latency than we see out of our Hive installations for larger queries. We need very predictable performance. This is a big deal compared to, this is a big reason we can't do this on Hadoop, is that the HDFS stack just isn't predictable enough. We don't get very consistent, predictable performance across our installations. But the single biggest is we need to be able to load data in 5 to 15 minute chunks. If you try and do this in an HDFS installation, You end up with too many small files. Small files give you bad performance, and it kills your name node because you have too many small files, and there's a whole complex thing you need to be able to do to load at that rate. We need short load times. We are not doing real-time loads, and we need the loads to be 100% reliable. Getting 100% reliable loads out of Hadoop, if you've ever done it, is extremely difficult. We have like 4 systems at Facebook that can do this, and you always either end up with duplicate data or missing data. It's a huge pain to do at scale. And to round it out, we're targeting tens of concurrent queries again, not dramatically huge concurrent loads on this. So the basic high-level architecture, very simply, like client sends the coordinator the query. We do our same parse and analyze. We have a plugin that's a custom connector that is reading its metadata out of a MySQL, and it knows where all of the data pieces are by, again, looking in a MySQL for the data pieces. Then we farm the work out to a bunch of workers that read from local flash. So very simple, high-level architecture. So this is the question we always get. But that's exactly what Hive does. Why don't you just use Hive? So the devil's in the details. We have a lot of features that we need to put in that are either difficult or impossible to integrate into a Hive solution. And in a Hive solution, of course, you would be taking on the burdens of HDFS and the Metastore. So we need full-featured DDL. This, like for anyone who doesn't work on Hive, who works on traditional database, like adding a column into Hive, yeah, you can add at the end, but if you want to remove it, then you have problems. And if you want to change the order of columns, you have problems. There's all sorts of problems with like basic DDL operations that work in any warehouse that is built here in Boston. So like we need real full DDL. We need table statistics aggregated at a level where we can quickly pick out the chunks of the tables that we're going to want to scan. This is to improve query performance, not for the query planning part. That's a different part of table statistics that we're working on. We need a tier storage system, which I'll get into. Again, we need the loads to work every time. And there are a bunch of additional physical organizations that we need to be able to do to hit our performance targets. So in the Presto Raptor system, a table is divided into shards, just like any other system would do. Each shard is stored in a separate file, a replication unit, so we can easily replicate the chunks around the system. Shard is typically 1 to 10 million rows, depending on the installation. They can be a bit smaller in some clusters that need extremely low latency, but they're typically 1 to 10 million rows. And all the node assignments and stats are stored in MySQL. So this is an example of how we're storing stuff. So on the left here, we have a table that says, okay, table 1 is orders. Table 2 is line items. Like, of course, this is how you abstract it. This is actually how you do full-featured DDL, is like, you don't put the names of your columns directly in the files, because that makes it hard to change them later. Anyways, pretty obvious. And then for each table inside of Raptor, we have a table inside of MySQL that contains a line, a row for each shard in the system, so each 10 million rows. And there's the nodes that it's on, and then a min-max of each column. This allows us to very quickly go and say, hey, if I'm looking for the files that contain Tiger, then it's only going to be this last shard. We instantly drop out most of the scans. This is like, a big win, easy to implement too, and works well with the way Presto works with connectors. We're able to push down these predicate summaries, turn these into range queries in MySQL, and instantly select out only the sections we need. So in the earlier picture, I showed you kind of like the high-level picture. I left out a part. So there's another tier in this system. So we have our coordinator talk to our workers. Our workers have a local flash tier. And then there's a second tier, which is our backup store that holds the durable copies of the data. So this system was designed to run on Flash to start with. We actually do have installations that are looking at doing this with large rated system, but this was designed for the first use case for Flash. We needed the IOPS for a very specific customer workload. But that customer, they could afford a lot of machines, but they couldn't afford enough machines to keep 3 copies of all the data in Flash. Flash is just way too expensive for us at the scale of this system. So we keep 1 copy in the local Flash, and then we keep 1 copy in a backup tier. And so currently internally we're using Gluster for this. Gluster's got a lot of problems. We're looking for another system internally. But this system can really be anything. The only thing we look for in the backup tier is we need to be able to do a put and a get. You don't even have to list files. Like, that's it. The system knows everything and where it's going to be. So like very, very basic from the system. It just needs to be durable. So this can be S3, this could be HDFS again, it could be anything. We're only using this when a node goes offline or we've done a reassignment, we can pull it back out of the backup tier. So it needs to be durable and available. So that's the basic extra pieces to the store system that we need to do. Couldn't do that with HDFS. Now I'm going to move on to how we actually get data into this system atomically. So what we have a system where internally we have this streaming system based on Scribe where we have events for things that are happening across the system, like anything. It could be like Presto queries are an event in this system. So we have a system that's based on Scribe similar to Kafka or Amazon's Kinesis. And the key point is that it provides a continuation token. So we rely on this continuation token design, and we do our loads using SQL. So let's show the next slide. So basically, we have a loader process that's going to periodically execute the query, insert into my target table by selecting the data out of my source stream, where the token is, where I left off to now, or now-ish, right? And that's all the system does. So the key to making this, so the loader process, the way we make this atomic and transactional is the loader process records, hey, I'm going to start doing a query to load this chunk, and I'm giving it ID 123. Then it submits that query to Presto saying this query has ID 123, and then we wait for that to finish. And we can check our ID, which we've pre-recorded in our system, to see if the thing's been committed or not. And then once the job completes, we record it's completed, and then we repeat. So there are a ton of things that can go wrong with this. So first of all, the loader crashes. Well, how do we know the state of any job we've submitted? So the first thing we do is, very clearly, we record like we're going to execute a job. So if we crash before the job showed up in the other system, we can go check, hey, what's the status of this query? And it says, I don't know. So we go and we just record it in that system. If you ever see a query with the tag 123, immediately kill it, it's dead. So we can poison the transactions moving forward. So once you have that, the rest of the things are pretty easy. You come up, you go look at your queries, and you just go cancel everything because who cares? It's only a 5-minute load anyways, or a 10-minute load. If a query hangs because it's taking too long, you can go and poison it. You can go and cancel it, and then you can check, hey, did I happen to cancel it in the millisecond before it actually completed and actually completed? So you can go back and check the state of this. The number one problem you have is duplicate loaders. This is a huge problem because you have a really big system, and you always have a system to go, okay, is the loader running? But the loader is unavailable because there's a network hiccup or something like that. So the system goes and says, okay, I'm going to start another one. The second loader starts up and starts submitting jobs, and then you get duplicates. Or it advances the tokens, and then you get a hole in the file in your stream. So this algorithm with the external IDs guarantees that only one of them is going to make progress, and pretty much neither one makes progress, and then you need monitoring to say, hey, we're not making any progress, and wake someone up and go kick the loaders. So that's it. Very simple. So to hit our performance targets, we're doing very basic organization of the system like any commercial warehouse would do. Actually, ours is super simple. A commercial data warehouse would do better than this. So we're organizing along temporal boundaries. We're assuring that our shards don't cross temporal boundaries. This is because at Facebook, pretty much everything starts with a time range query. You aren't going to go and search data from 90 days ago to show a chart that just has yesterday. But more importantly to us, like all our data has to have retention policies. So we are always loading at the front and we're always deleting at the back. And we don't want to have our deletes be expensive or annoying. Like they just need to work and be quick. So splitting along our temporal boundaries makes all the retention stuff really easy. And then we're also organizing each local shard. We're sorting it so that we can internally pick out the sections inside the file that apply to the query. But we're also, this can also, in combination with the compaction algorithm, reduce the actual shards because we're narrowing the range for just a couple of the columns. So this is kind of a diagram of like what we end up doing. So we have two different temporal boundaries going up. So let's say these are just days. And then we just have a bunch of files that were loaded and they may be overlapping or not overlapping in terms of our sort columns. So we have a compaction process that goes through and selects a chunk of these shards that are overlapping and runs a query to, runs a query to write new files that have so that none of these shards overlap. So if you show the next picture, we end up with, by day, we end up with these non-overlapping sections. So when we go to look for something that's range bound by our sorted columns, we only pick out a couple of these shards. This also, one of the problems with doing 5-minute loads, as I said before, is you end up with small units of work. And so if you're loading a very small stream and you're loading every 5 minutes, you might actually only have like 10 rows because it's just a small data stream. So this allows us to compact them to, the Goldilocks size, where they're not too small that we end up spending all our time in overhead of like opening all the files, setting up the whole execution, tracking that, and not so large as like you basically run on one CPU core and it's a billion rows, so it takes forever. So very simple organization background system. We have a bunch of other ones to balance nodes across data files across the nodes. When a node goes offline, to eagerly copy down, because if we go and like a shard's missing when we go to execute a query, we'll go and fetch it out of the backup store live. But you kind of want to do it ahead of time. In this case, all the production installations of this, they're flash, so you're talking just a couple of terabytes of data. So it isn't a huge deal if a couple nodes go offline to read out of the system. But if it's a big disk system that has 15 6-terabyte disks, you're going to want to get this done as quickly as possible. And then there's a garbage collection system to clean up all the junk created by the compaction system and users deleting stuff and junk like that. That's just kind of like a very quick intro into some of the things we've done in the Raptor system. This is in production at Facebook. We have a fairly large installation of this for a couple of important customers. Actually, we have 4 installations? Something like that. 5? Okay, we have 5 installations. So we have a bunch of these. There's some additional places where we plan on using this technology. So the biggest one is a hot data cache for our Hadoop data. So you can kind of think of Raptor as being like a caching tier for the backup tier. So we have a plan to try using this to be able to bring down the hottest data sets to the local Flash installation. So this would be a change to where we have 0 to n copies of the data. And because if it's really hot, you're going to want a couple of these systems so the concurrent queries can work on it. So that's a thing that we plan on trying out maybe into this year, early next year. But we also have a plan to build a query result cache because we have a ton of dashboard installations at Facebook where people are running these expensive queries every 10 minutes, even though the data isn't really changing. And we have a way for people to cache stuff, but no one implements it correctly because it's actually really hard to implement a good query cache. So we've decided that we're just going to do this and build it into Presto so it just works every time. And that store would be in the Raptor technology by default in our installations. And then, so in the system that Martine was talking about, they used to Sharded MySQL. Sharded MySQL is awesome, very performant, super low latency, super reliable. We cannot afford to keep the raw data for those installations in MySQL. So they're rolled up data, but they need to also be able to slice and dice the data. So you have you have some users who are most users are gonna hit the rolled up data. We have some customers that need to actually be able to run against the raw data. So we're gonna build a system where we keep the roll-ups in the Sharded MySQL and the raw data inside of Presto. And then we'll have like 98, 99% of the queries going to the roll-ups. And then for those couple of important people that need to hit the raws, they'll be able to hit the raw data and do new calculations. And you would think of that then moving forward, we'll be doing the roll-ups directly inside of Presto, and that's a materialized view system. So moving towards that direction, again, the raw stores are most likely Raptor, where the smaller, higher performance stuff would likely be Sharded MySQL for a while, but as things go, it'll probably all just be Raptor for us. So, I think that's it. All right. We have time for questions? Yeah. We have time for a couple of questions. We need to get some mics back there. Someone have.
I have a question on Presto. You mentioned about SQL sorting. Is that handled by Presto, or you have to handle it separately?
So can you repeat the first part?
Sorting the database, MySQL. Would you
sharding.
Would you be handle that within Presto, or you have to set that up separately?
No, so there's actually that's part of what the MySQL team manages. They have the infrastructure to, you basically create a cluster of machines and you say, I want to have so many buckets, and they figure out how to distribute the buckets across machines, how to move them around when machines fail. The only thing Presto needs to understand is how many buckets are there and where is the cluster, and then Presto is the one that figures out. We're gonna take so when the data gets loaded, we figure out where a given row is gonna land, and when we query, we know we can push predicates down into the connector, and the connector can figure out, oh, for this predicate, I only need to touch these shards and not the others, and so on.
Thank you.
Excuse me, what is your hardware stack for all these petabytes and millions of queries?
They're just generally Linux computers. So for the warehouse, they're mostly like, so we have different generations of hardware. So they're all like, a couple of CPUs, a bunch of memory, and then a ton of disks. Yeah, I mean, it looks like kind of everyone else's. Like, I mean, there's just a lot more racks,
Yeah,
but.
So I don't think we can't talk about the specifics of the amount of memory and this kind of that. What we do have is, for different deployments, we have different footprints. Like we have, in the case of the warehouse, we have machines that are heavy on disk and have a reasonable amount of memory. For Raptor, we have machines that have flash and a lot of memory, because we also want to do big queries and big aggregations and joins and so on. So we try to pick we have a few options in terms of what we can pick, and we try to pick the ones that fit the specific deployment and use case.
And then, I mean, we have generations of hardware. We have machines that are, 3-4 years old, and we have machines that are brand new. The brand new ones are amazing. If your data's in the cluster with the new machines, you're super happy. It's so much faster than the machines that were 4 years old. So, Like, kind of depends.
Yeah, hi. Do you integrate with Cassandra? If the data is in Cassandra, does that get pulled into MySQL, or how does that happen?
So we have a connector for Cassandra. There are not a lot of people using it, so when you do go to use it, you'll probably find some issues. But it's a connector that goes directly to the Cassandra ring and pulls the data out in parallel. So it was contributed by a couple guys in Germany. DataStax helped out with it for some, but it's not deeply used.
We don't use it at Facebook, so.
Yeah.
So a lot of your performance comparisons were saying, okay, a lot of your comparisons for performance were saying, okay, this is much better than Hive. Are you also looking at the progress of technologies like Impala or Spark SQL or Hive on Spark?
So, it was earlier this year. We did some analysis against Impala. It's a pretty good system. I think the biggest difference for us is when we go to, so when we go to do an analysis, like for us, when we are going to compare, like these other systems, like they're never going to run inside Facebook. Like the scale we need to run at and the reliability we need to run at, like being able to go and run any of these other systems, it's just not going to happen. We have Presto. So the only reason we do it is what we're looking at is, are they better in certain areas? And then we can focus on that area. Because if they're better in an area, then we have places we can get better. And we're always trying to figure out how we can get better at these things. So we did an analysis against Impala. Impala's pretty good, and we found our performance was about on par. But it depends on exactly what you're doing. So the data formats really matter. The way Impala works best with Parquet and is really not good at anything else. It matters on the queries you send it. Some queries it's good at optimizing, other ones it's really bad at optimizing. If you send it highly selective queries where we have information out of ORC, we kill their performance because their lazy reads and their predicate pushdown was non-existent at the time. They may have fixed it, I don't know. But so and then every time we do an analysis, it takes a very long amount of time. The other ones like Drill, I know almost nothing about Drill. We don't really hear about it a lot. I don't know. Do you have other?
Just to follow up on that question on the format. So just to clarify, you guys run this. The backend is MySQL. You guys are not running Presto on Hadoop per se, right? Is that a true statement, or?
For which workload? So we have different use.
When you presented your Presto, the SQL engine on the back end, are you running against Hadoop?
So in one case, so in the first part,
Explain connectors.
yeah. So Presto is the query engine, and it has a connector interface. The connector presents to Presto an abstraction of what tables they have available, what columns, and what data types they have, and then how do you access the data in wherever it's stored. One of the connectors is a connector that can talk to the Hive Metastore for the metadata and to HDFS for the actual data, that's what we use for our Hadoop warehouse. We have Presto running against the Metastore and the Hadoop and HDFS, but it bypasses MapReduce. We don't use MapReduce for that. In the other use case, where the second part I talked about, it's Presto there's a connector that integrates with sharded MySQL, and there's no Hadoop in the mix there.
Got it. Okay.
Yeah, and then the third connector that I talked about, that's local Flash, and then there's metadata that's stored inside of a MySQL, very similar to the Hive Metastore, but completely custom. No Hadoop involved in that either. Any other questions?
I wanted to clarify, someone asked, when Christina was up here, they asked about whether we use the surveys or not from Hive. And the answer is, in most cases, we don't. We have specialized readers for ORC, for Parquet, and for RC. Yeah.
The RC one isn't checked in.
Okay, we
Still
will
in
have
review.
one for RC.
So you guys have readers for those different formats?
Yeah,
Are
yeah.
those open source with Presto?
Yeah,
as
they're
well?
part of the code base. Yeah.
It's why the performance over Orc in those, the ones where we have custom readers, the performance is significantly better. It's like 4x better.
Okay.
But it will fall back to whatever readers are available in the Hive code base if we don't have a specialized one. Like for example, a text input format, we pick whatever is available.
Cool. Excellent. Thanks.
So what differentiates the Presto from the Hive? That is because Presto is can run the interactive query and performance backup.
What's the difference with that?
Yeah, what?
Oh,
What differentiates Presto with Hive?
do you want to take that one?
Well, so Hive is a front end to MapReduce, and when you write a Hive query and run it in Hive, it translates it into a set of MapReduce jobs, and because it uses MapReduce, it has certain constraints and certain assumptions about the execution model. Like, in particular, MapReduce is very pessimistic about like whether you're going to have failures, and it tries to protect against every possible failure that can happen in the cluster by persisting all the intermediate data to local disk between every step. And you end up paying a lot of latency, I/O latency doing that. Presto only reads data from storage and produces, and if you write a query that writes back to Hadoop or some other storage, it will write it on the other end, but it streams and executes everything in memory in between. So you end up saving a lot of latency from that. There's let's see, other things that we do. For example, we compile expressions to bytecode to make it easy for the VM to generate machine code out of that. Hive interprets expressions, so there's going to be a difference in CPU efficiency from doing that. And there are a bunch of other optimizations that we have in place that make it faster.
I mean, the big summary I think is Presto is a very traditional data warehouse, distributed data warehouse design. Hive is impressive in that it took SQL and converted it to MapReduce. It's impressive that they pulled it off at all. It's extremely difficult. We took a very traditional approach, and that's why we get very different performance numbers than what the MapReduce system was doing.